Today's lesson is on improper integrals. But before we start, we need to go back and talk about limits as our variable approaches infinity. So to do this, I have some different examples and some graphs, and we're going to go through so you can get an idea of which functions will have a finite limit and which ones would have an infinite limit. So when we look at this first one, we have the limit as b approaches infinity for 1 over b. Now you're used to x's, but we have b's here because it's going to be useful later on in our lesson. So here's our function, 1 over b. Okay, and we want to know as b goes towards infinity, as we go towards infinity, what does 1 over b get closer and closer to? In this case, it's going to get closer and closer to 0. And this makes sense because as you divide by bigger and bigger numbers, you're going to get smaller and smaller. So you're going to have like 1 divided by 1,000 is small, but 1 divided by 1,000,000 is really small, and 1 divided by 1,000,000,000 is even smaller, etc. So eventually, as you keep dividing by bigger and bigger numbers, you'll get to 0. Or like 1 over b squared, so here's the graph for 1 over b squared, and you can see again that as b goes towards infinity, 1 over b squared is going to go towards 0 because we're still dividing by infinity, but our numbers are getting even bigger, even faster, so it just goes to 0 even faster. Or we can have the function 1 over e to the power of b. So this would kind of be like 1 over e to the infinity. And if you think about it, e raised to the power of infinity, that's going to be even bigger numbers. So this is like e raised to the power of 1,000, e raised to the power of 10,000. This is getting really big, really fast. So this limit is going to be 0. It's going to go towards 0. Or even 1 over the square root of b. The square root of b, those numbers aren't going to get as big quite as quickly, but we're still going to have 1 divided by the square root of 1,000, 1 divided by the square root of 1,000,000. Eventually, the limit is still going to go towards 0. So you can kind of see any time we'd be dividing by infinity or dividing by really big numbers, it's going to go to 0. And just to show you, occasionally we might want to find the limit as b goes towards a negative infinity. So this means we'd actually be going towards negative infinity. We want to go this direction instead. But even if I'm dividing by negative numbers, I'm still going to get very close to 0. It's just on the negative side instead of on the positive side. So these are all functions where the limit as b goes towards infinity is going to be 0. And that's because, again, we're dividing by some form of really big numbers. And when you divide by really big numbers, you get 0. Okay, now on the other hand, let's look at these. If I just take the limit as b goes towards infinity, notice, as b goes towards infinity, we're going to go towards infinity as well. Or if we do b squared, we're just going to get bigger numbers even quicker, and we're going to get to infinity even quicker. Or e to the power of b, once again, it just keeps going up and up and up, so we're just going to go towards infinity. Square root of b, the numbers don't get as big as fast, but eventually we still get super big numbers, and our limit is infinity. Or natural log of b, again, we grow a little bit slower, but we're still going to go to infinity eventually. Okay, so here's where you can compare and contrast. Anytime in this class, because in this class we keep with pretty simple functions, in this class, anytime you divide by infinity, you'll get to 0. If you're not dividing by infinity, almost anything else you're going to come across in this class, the limit will be infinity. So with that in mind, let's actually find some of these limits. This is what will be most pertinent to what you're doing today. So let's find the limit as b goes towards infinity of 1 over 5 plus 7 over b plus 10. Okay. So when I do these, it's not technically correct. You're not really supposed to write infinity in your calculations, but we can do it just to kind of get an idea of what's happening. So this is going to be like 1/5 plus 7 over infinity plus 10. Now, if you have infinity plus 10, that's basically going to be like infinity, right? And if you have 7 divided by infinity, that's going to go to 0. Even though 7 is bigger than 1, if you still have 7 and you divide by really big numbers, it's going to go to 0. So this limit is going to be 1/5. And this next one, let's go ahead and plug in the infinity. So 3 minus e to the negative 7 times infinity squared minus 2. So this is going to basically be about 3 minus e. Okay, Now let's see, infinity squared is just going to be infinity. Minus 2, we really don't care about that because infinity minus 2 is still going to be infinity. But this negative 7, that negative means that we're going to have it continually be negative. So this is kind of like e to the negative infinity, or because it's a negative power, 3 minus e to the infinity. Now we're dividing by e to the infinity or dividing by really, really, really big numbers. So this entire thing goes to 0. So we get 3. So this term, again right here, as b goes towards infinity, that entire term goes to 0, so all we're left with is the 3. And example 4, find the limit as b goes towards negative infinity of 5 times 1 minus b to the negative 2/3. Let's rewrite this. Before I even plug it in, I'm going to rewrite it. This is 5 times 1 minus that b to the negative 2/3. I'm going to write as 1 over b to the 2/3. It just makes it a little bit more obvious now. Okay. Now let's go ahead and plug in our negative infinity. So this is going to be 5 times 1 minus 1 over negative infinity to the 2/3. Now, we're dividing by an infinity. It doesn't actually matter if it's positive or negative infinity, because this just means that we're going to have negative numbers. Okay? But we're actually going to square them here, so they're actually going to become positive anyways. Either way, we have really, really big numbers, whether they're positive or negative. They're really big numbers, and we're dividing by really, really big numbers. So this piece goes to 0. And all we're left with is 5. This next one, we have 2e to the 7b, so 2e to the 7 times infinity. Or this would just be 2e to the infinity, because infinity times 7 is still infinity. So notice here, I'm not dividing by anything. This is just e to the infinity. So if I was to graph it, it looks like this. Okay. Or if I graph e to the x, it looks like this. So notice, I just have really big numbers. I'm not dividing by them or anything. I'm just really big numbers. Times them by 2, it's still really big numbers, so I'm going to get infinity. Okay, so this was actually an infinite limit, not a finite one. Okay. So sometimes as you do it, you'll get an actual number. This is a finite limit. This is an infinite limit. And sometimes you'll get finite ones, sometimes you'll get infinite ones. That's okay. But now, let's find areas under the curve. So what if we wanted to find the area under this curve of y equals 4 over x squared from x equals 1, so here's my x equals 1, all the way to the right. So when I say all the way to the right, I mean I want to keep going for infinity. So I truly want to find the integral from 1 to infinity of 4 over x squared dx, because that's how we find areas under the curve, is we take the integral. But I want to go from 1 all the way up to infinity because I want to find the area all the way to the right. This does have lots of applications, especially in statistics. So we don't know how to find this integral yet. So let's start with, instead of doing it to infinity, let's look at the integral from 1 to b of 4 over x squared dx. And we'll just say, here's b, and then we can kind of keep moving that b further and further along until we get closer and closer to infinity. But first, let's find the integral. So the integral of 4 over x squared, that's really the integral from 1 to b of 4 times x to the negative 2. Okay, so with that in mind, this is going to be 4. X, if you raise it by 1, it's going to be negative 1 over negative 1, evaluated from x equals 1 to b. Okay. Or this is 4 over x, negative 4 over x, evaluated from x equals 1 to b. So if we plug in the top limit first, this will be negative 4 over b minus negative 4 over 1, or negative 4 over b plus 4. So what we want to do is we say, okay, well, we know what it is for any value of b. Let's try it out for bigger and bigger values of b. So you can see down here I made my table. We have values of b. I put in, here's my area of the 4 minus 4 over b that we found. If b is 10, then my area is 3.6. If b is 100, my area is 3.96, and for 100,000, 3.9999996. So what do you think will be as b goes towards infinity? As b gets bigger and bigger and bigger and goes to infinity, it looks like these numbers are getting closer and closer and closer to 4. And we can actually work this out officially by doing limits. So what we do is we say, I wanted to truly find the integral from 1 to 4 of the 4 over x squared dx. But to do this, mathematically, to be technically correct, we instead write this as the limit, okay? And instead of integrating from 1 to infinity, we integrate from 1 to b. And then we say what happens as b goes towards infinity. So this is why we practiced all of those problems where b went towards infinity. Of 4 over x squared dx. Now, we already found that integral up above. So we just need to now find the limit as b goes towards infinity of 4 minus 4 over b. So I'm going to have my 4, and it's going to be minus 4 over infinity. Okay. So if you think of 4 over infinity, we're dividing by really, really, really big numbers, and when you divide by big numbers, it goes to 0. So my answer is 4. So that means the area is 4. Okay. Now some areas, like this, because my line kind of went down and the line's going to get closer and closer to 0, I can find this area underneath it. There are some times you might have an example that looks like this. And let's say you're trying to find this area from here all the way over to infinity. Do you think you could find that? No, because it's just going to keep getting bigger and bigger and bigger, and no matter how far over you go, it's going to get bigger and bigger and bigger and bigger. So this area can't be found because it would be infinitely big. So this could be like the integral from 1 to infinity of e to the x dx. That one would be infinitely big. You wouldn't be able to actually find the area because it's never going to stop. It's just going to keep getting bigger and bigger. Whereas up here, notice the line function came down and the area gets smaller and smaller and smaller and smaller, so you can actually find this total area. So let's make this official. In our improper integrals, if we want to take the integral from a to infinity of f of x dx, we technically have to instead do the limit as b goes towards infinity of a to b f of x dx. We call it an improper integral because it has infinity as a limit. If we get a finite number out of it, we say the integral is convergent. If we get infinity, we say it is divergent. So let's try some examples. Let's find the area under the curve y equals e to the negative 2x for x greater than 3. So that means for our area, we're going to go from 3 to infinity, because they didn't give us a stopping point, e to the negative 2x dx. So technically, again, this is the limit as b goes towards infinity, and we'll integrate from 3 to b, e to the negative 2x dx. So we'll still have the limit. That stays with us until we actually plug in the infinity. And when we integrate, we get e to the negative 2x times 1 over negative 2. That's how you integrate exponentials. And we need to evaluate that from x equals 3 to b. So I still have my limit here. You have to write it quite a few times. So let's see. If we plug in b first, this is going to be negative e to the negative 2b over 2 minus negative e to the negative 2 times 3 over 2. Okay, let's see what we can do here. These will become positives, or plus. This e to the negative 2b, let's rewrite this as negative 1 over 2 times e to the 2b. With that negative exponent, we move it to the bottom, plus e to the negative 6 over 2. And we can go ahead and move that to the bottom as well. So 1 over 2 times e to the negative 6. Okay. Now we can plug in our infinity. So this is going to be negative 1 over 2e to the 2 times infinity plus 1 over 2e to the negative 6. Okay, notice this is, we're dividing by really big numbers. Okay, so anything divided by really big numbers, no matter what it is, always gives you a 0. So we're just left with 1 over 2e to the negative 6. And that would be the area under the curve for x greater than or equal to 3. Notice this is an actual number, so we would say that the integral is convergent. Sorry, the only thing I did is I moved that negative exponent down to the bottom and then I kept it negative. That should be a positive, e to the positive 6. Now this next one, let's do it again. We're going to now do the improper integral from 8 to infinity of 3 over x minus 6 squared dx. So first we have to rewrite it with the limit as b goes towards infinity, and we'll integrate from 8 to b. Now I'm going to rewrite this as 3 times x minus 6 to the power of negative 2 dx. Now technically, to find the integral with this x minus 6 part, you should probably use U-Substitution. But if you remember in our last video, I mentioned that our textbook says if the derivative of u is just going to be 1, they don't bother doing U-Substitution, because in this case we'd say u equals x minus 6. The derivative of that is just 1. So we can kind of just skip that, and if we know that the derivative would just be 1. So we're kind of doing U-Substitution. If you don't believe this or have a hard time with it, go ahead and do the U-Substitution out all the way. So this is going to be, we keep the 3 there, and then it's going to be x minus 6. We'd raise the power by 1 and divide by a new power. And we need to evaluate from x equals 8 to b. Now right here, I can see that I just forgot something. Technically, on every single step, we remember to write the limit because we haven't taken the limit yet. So this is going to be the limit still as b goes towards infinity. So I'm going to rewrite this quickly just to make it easier. This 3 times the negative 1, so this is going to be negative 3, and x minus 6 to the negative 1 over x minus 6. So let's write it like that. And we need to evaluate it from x equals 8 to b. So we still have the limit. Let's plug in the b, so negative 3 over b minus 6 minus negative 3 over 8 minus 6. Now we can plug in our b's, negative infinity, so we're going to have our positive infinity, negative 3 over infinity minus 6. Minus and minus, this is going to be plus 3 over 8 minus 6 is 2. So notice right here, we have something, doesn't really matter what, something divided by really, really, really big numbers. So anything divided by really, really big numbers goes to 0. So my final answer is that this is 3/2, and because I got a specific finite answer, we could say that integral is convergent. Our next example, let's calculate the integral from 4 to infinity of 1 over the square root of x dx. So let's rewrite this. The limit as b goes towards infinity, the integral from 4 to b, and instead of 1 over the square root of x, I'm going to write x to the negative 1/2 to make it easier to integrate. So this will be the limit as b goes towards infinity of, okay, now x to the negative 1/2, we raise it by 1, so we have 1/2, divide by your new power, evaluate from x equals 4 to b. So we still have the limit. I haven't plugged it in yet, so I have to keep writing it. Okay, now plug in your b, so we'll have the square root of b, and instead of dividing by 1/2, let's just write that as a 2. So 2 times the square root of b minus 2 times the square root of 4. So in this case, we're going to have 2, if we plug in the infinity, 2 times infinity, minus 2 times the square root of 4 is just going to be 4. Okay, notice right here, 2 times the square root of infinity, we're not actually dividing by big numbers, we're multiplying by big numbers. So our numbers are just going to keep getting bigger and bigger and bigger and bigger and bigger, and they never get smaller. They just keep getting bigger and bigger and bigger and bigger, no matter what we do. So we end up with infinity. Because we ended up with infinity, we say that this interval is divergent. We cannot actually find the area underneath it because it doesn't get small enough fast enough. If you were to graph this, it would look something like this. Okay, and so you'd be trying to find the area from 4 to infinity. And it kind of looks like it's getting smaller, but it actually doesn't get small enough. It keeps adding on more and more area. Okay, and you keep getting more and more area, and so that area underneath it eventually still gets to infinity, and so we can't find that area underneath it. So once again, this is an integral. We'd say our final answer is that we would say it was divergent, and then we can't actually really find a number. Instead, we would say it is divergent as our final answer. Let's try another one. Let's evaluate from negative infinity to 0, e to the 7x dx. Now technically, this doesn't really matter which letter you put here. You can do any letter you want. But this negative infinity, we need to replace it with a letter. In our textbook, they will replace it with an A because usually they say limits go from A to B. So they'll put an A there, but if you want to put a B there, it's not going to make a difference. So we're going to go from A to 0, and this will be as A goes towards infinity, e to the 7x dx. Okay. So to integrate this, the integral of e to the 7x is e to the 7x times 1 over 7. And we want to evaluate this from x equals a to 0. So we still have the limit until I actually plug it in. We have to keep my limit there. So we plug in the 0 first. This is going to be e to the 7 times 0 times 1 over 7 minus e to the 7 times a over 7. So this is still the limit as a goes towards infinity. E to the 7 times 0 is just going to be 1. So we just have 1 over 7 minus e to the 7a over 7. Okay. Now, okay, come all the way back. This was a negative infinity. Let's fix that. Just got in the habit of writing infinity. So this is a negative infinity. So negative infinity, negative infinity, negative infinity. Okay, so we're going to have 1 over 7 minus e to the 7 times negative infinity over 7. Okay. Now notice here you have a negative in the exponent, so we need to rewrite it anytime we have a negative in the exponent. So this will be 1 over 7 times e to the 7 times now positive infinity. So we have 1 divided by really, 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 really big numbers. So that goes to 0, and we just get 1 over 7. Because we got an answer, this is convergent. A finite answer is convergent. And our last remark, okay, if you want to find the integral from negative infinity to infinity of f of x dx, so this would be, in statistics, there's a really famous curve called the bell curve, or the normal curve, and it looks something like this, and you want to find the area under it all the way from the negative infinity all the way to positive infinity. Okay, so it does have applications. You want to find the area under this entire curve. But as far as calculus goes, if you want to integrate it, you split it up as two integrals from negative infinity to 0 and 0 to infinity. And you do each piece separately. So here's one example. We want to integrate from negative infinity to infinity of e to the 7x dx. Notice that's what we just did right here. Okay. Except here we did negative infinity to 0. Now we want to do it all the way to positive infinity. So this is going to be the integral from negative infinity to 0, e to the 7x dx, plus the integral from 0 to infinity, e to the 7x dx. Okay. We did this piece up above. We know this piece is 1/7. So let's focus on just this piece for a minute. So let's do the integral from 0 to infinity, e to the 7x dx. This will be the limit as b goes towards infinity of the integral 0 to b e to the 7x dx. Okay, we know the integral is going to be e to the 7x over 7 evaluated. Oh, I forgot to write my limit again. You have to be careful. So the limit as b goes towards infinity of e to the 7x over 7 evaluated from x equals 0 to b. So we still have our limit. Plug in the b, so e to the 7b over 7 minus e to the 7 times 0 over 7. Now plug in your infinity. So this is going to be e to the 7 times infinity over 7 minus 7 times 0 is just 1, so 1/7. Okay, now this e to the 7 times infinity, notice we're not dividing by big numbers, we just have really big numbers here. So these big numbers keep getting bigger and bigger and bigger and bigger and bigger, so this entire thing is just going to go towards infinity. So infinity minus 1 over 7 is just infinity. So this part is divergent. Okay, and so when we come back and look at our entire integral, this first piece we found up above, this first piece is 1 over 7, but this piece is infinity. So what happens if you have 1/7 plus infinity? We're going to get back to, once again, just infinity. So because one piece was divergent, the entire thing is divergent. So the integral from negative infinity to infinity of e to the 7x dx is divergent. Because one piece converged, but one piece diverged, so the entire thing now diverges. Because if you try and add 1/7 in infinity, you still get back to infinity.